A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians! Welcome back to the first video of the week. I really need to slow down with videos in the last time. Teaching full-time as a teacher and having a lot of side projects going on right now. I just can't afford to put as much time into YouTube as before right now. So excuse me for that, but still one video per week. And don't forget to check out Stanford. We got the engineering watch now going on over there, link in the description. And today we are going to take a look at something that a subscriber asked. Do you remember back in the good old Fable Maths days where I still asked in each and every video who would win? Some chat or the something boy, and the boy always won. And today we are asking ourselves the same question once again. Who is going to win? The differential of log to the base x of 420 or the integral of log to the base x of 420? You decide at the end of the video which one you found more satisfying, cooler, etc. And now please see the difference here. We got functions with respect to x, obviously. We want to differentiate or integrate something. But it's not a regular logarithm, you could say. Our argument of the function is being defined as the base down here in the logarithm. So we really need to pay attention here what we are going to do, step by step. And at first a tiny little refresher on logarithms and what they are and how you can basically make a change of base, or how you can convert each and every logarithm to any base into some kind of natural logarithm, for example, or any other logarithm of any base at all. So at first there was counting 1 plus 1 plus 1, okay, and this was kind of a hassle to count up to 5. This really took a long time, so we defined addition, okay, using successors. But then we had a situation, what happens if we want to count together 5 plus 5 plus 5? This is also a hassle, so mathematicians introduced multiplication. This is 3 times 5. But then what happens if we have 5 times 5 times 5. Oh, this is also a hassle if you want to calculate big numbers. So mathematicians came up with exponentiation. But what happens if we have a big O exponentiation? It's going to get messy really quick. And to get a better overview of exponentiation, mathematicians made their life easier in the 17th something century, if I remember correctly, by introducing the so-called logarithm. So imagine we have something a to the b power being equal to c. Now the thing is, for given a and for given c, for example 2 to the b power is equal to 8, how would you find out b? I mean, obviously 2 to the third power is going to give you 8, but is there a formal process to get yourself the exponent up here? You can take the logarithm base a on both sides, by definition of the logarithm, to get yourself the value for b. Because there could be situations like 2 to the what power is going to give you 9. This is weird. I mean, 9 is not a multiple of 2, so this doesn't work out nicely. So we need to get the logarithm in place somehow. Meaning, if we were to take the log a on both sides, log to the base a of a to the b power, by the logarithm rules, we can bring the b to the front. Okay, this is pretty easy to prove for natural arguments, a bit harder to prove for continuous arguments, you could say. Meaning this is going to turn into b times the log base a of a, and by definitions of logarithms, log to the something base of the same something is going to turn into 1. This is just like with the natural log of e, this is going to turn into 1. And also we need to apply this function to the other side too. Meaning this is just log base a of c. So in order for us to find out what the solution to 2 to the b power is equal to 8 is, we are just going to say, okay, b is going to be defined as being the logarithm, in our case of 2, of our number 8, in our case c. Yeah, and this is how you go about using logarithms. But behold, logarithm base a of c is not the only logarithm where all those logarithm rules apply. And now what we could do is we could say, okay, I don't want to use the logarithm base a here. This thing sucks. I don't want to use it. Logarithm base 2, I mean, who wants to use log base 2? This is just absolutely stupid. No one uses binary log. Am I right, programmers? Why not use log base e, because e is basically also 2. We are going to use log base e, meaning the natural log on both sides here too, and then a bit of magic is going to happen. Meaning, and just for once I'm going to denote it using ln instead of log, because otherwise it would be a bit confusing for most users out there. Meaning I'm going to take the ln on both sides, so ln of a to the b power. By the logarithm rules we can drag the b to the front yet again, giving us b times the natural log of a. It's nothing other than, natural log of c. And now, what we can do is we can solve for b right here, meaning we can divide both sides by ln of a under the condition that a is not equal to 1, hence the logarithm would turn to 0, meaning b on the one hand is now the natural log of c divided by the natural log of a, but also, hey, b is exactly the log base a of c, meaning if we were to plug this in, we also get a relationship between the logarithm of any base, of any argument, with regards to any other logarithm. It doesn't need to be the natural log, for example. It could be any other logarithm, actually. Okay, you can apply log base pi, for example, on both sides and get to the same result. Meaning, logarithm base a of c is the same as the natural log of c over the natural log of a. But I was choosing the natural log here on purpose, because the natural log is defined as being the inverse function to the exponential function, and using implicit differentiation or just integration in general, we can easily find out what, for example, the derivative of the logarithm is. Or by using special functions, we can also find out what the integral of the logarithm of something is. I mean, this logarithm, as you might notice here, if we plug in x now, is going to be 1 over the logarithm. Okay, natural log of a, for example, natural log of x. Hence, we need to use special functions in the game. But at first, let's take a look at what log x, log base x of 420 actually is, by using this definition right here. Okay, this also means that log base x of 420 is the same as, okay, 420 is going to go up here into the numerator, into the natural log, divided by the natural log of x. And now you might see what I'm talking about, because this is actually a function that we talked about before, 1 over ln of x. If you want to integrate this, this is going to turn into something which you can only compute numerically, basically, except for a few particular values by using upper and lower bounds. But at first, let's take a look at the differential. I mean, this right here was the groundwork, was good, okay, pretty easy, just a little refresher, and now we can get started with the real deal. Namely, we are going to take a look at the derivative of log base x of 420. I mean, by plugging the new definition right here in, we are going to get the differential in x of the natural log of 420 divided by the natural log of x. And I mean, natural log of 420 is just something. I don't care what it is. It's just constant. We can bring it to the front, leaving us with just, and then we get in the differential 1 over log of x. This is the same as log of x to the negative 1th power, basically. So right now we are at the point where we say the natural log of 420 times del x of the natural log of x to the negative 1th power is the same as the differential of our original function. And now we can just basically make use of the chain rule right here. This is just using the chain rule. Namely, what we are going to do is at first the power rule, okay, on the outer derivative. We are going to drag the exponent to the front, the negative 1. We are going to reduce it by 1, gives us negative 2. So leaving us with natural log to the negative 2th power, negative squared, and then we need to take the inner derivative, and the inner derivative of the natural log is going to give us 1 over x. So in conclusion, we now know that the derivative of our weird function that we have right here is going to turn into the natural log of 420, dragging the negative 1 to the front, so negative natural log of 420 times 1 over the natural log of x, but the thing squared, this was natural log of x to the negative 2th power times the inner derivative, which is going to be 1 over x. And now we can just make use of some logarithm rules. For example, negative ln of 420 is the same as the ln of 1 over 420, leaving us overall with a differential of the ln of 1 over 420 divided by x times ln squared of x. And this right here is the derivative, pretty easy. Differentials in general are very easy to compute most of the time if the function is differentiable. Yeah, and this is basically it. This was the first differential, or the first part, okay? This was the first contender in our match right here. Now what about the integral? The integral is, like mentioned before, tiny little bit ugly and only works for few particular values, basically, as upper and lower bounds, because the function that we are going to have is going to diverge pretty quickly. It's a function that tends to diverge very, very quickly on upper and lower bounds, and if we were to plug our definition for log base x of 420 in, we are going to get the natural log of 420 divided by the natural log of x, integrate with respect to x. And once again, ln of 420 is just a constant. By using the linearity of the integral, we can bring it to the front, leaving us with the ln of 420 times a beautiful integral, no, that's not a beautiful one, I'm terribly sorry for bragging, dx divided by natural log of x. And what we got here is exactly what I was talking about. This right here is the logarithmic integral. I made a series on special functions like the cosine integral and the sine integral. You can find the link to the number theory playlist down there in the description. Leaving us with a final answer of the natural log of 420 times the logarithmic integral of x. It's an indefinite integral plus some arbitrary constant. Let's go with kappa yet again. And this right here is the probably not so satisfying answer to the integral boy this time. And yeah, I hope you did enjoy what you have seen today. I certainly like this question because yeah, it got me thinking that it's actually pretty cool to think outside of the box a tiny little bit, even with logarithms. We are so used to using just logarithm-based e, so the natural log, that we kind of tend to forget how it is to deal with just logarithms of any base at all. And if you have an example like this, it's actually a nice refresher for just getting back to all the tools that you needed to deal with any logarithm in the first place, like this change of base rule for logarithms, which is one of my most favorite rules in mathematics overall, which I really like. And if you did enjoy what you have seen today, maybe you would also enjoy the contents of today's sponsor Brilliant, who were kind enough to sponsor yet another video here on this channel. And seriously, they got a lot of logarithm questions and chapters in their courses over on their website. And if you want to learn more about what we did here today, then definitely make sure to check their website out. If you're not yet familiar with Brilliant, then I'm going to give you a short and spicy introduction, because Brilliant is this one online source for learning that you should definitely try out if you want to learn something new, at least in the STEM field, be it mathematics, physics, programming, chemistry, whatever it is you want to learn. Brilliant has something up their sleeve for you, and they actually pack it nicely into very well thought out courses, which I really enjoy the most on their website. Overall, they are on the one hand an online learning platform, and on the other hand mobile app, so you can use it on the go, learn something new while being in the bus, for example, which is pretty cool in and of itself. And they basically have their greatest strength in their interactive learning experience. Interactive courses, nearly 70 at that, which is a pretty huge number if you think about it. And if you go into their linear algebra course, for example, you're going to have content for a few hours worth. Okay, it's pretty crazy. Many courses over there, and you really need to spend a lot of time on the courses to get a real feel for the intuitive explanations that they give you, and just the way they teach you all the things that you want to learn in this course is just overall pretty good. And I, as a teacher, really have to say they did a good job packing everything into nice portions over on their website. It's very didactic. Most of the time very short explanations, but right on point, right on spot, and it's really good feeling working through their courses, and you should definitely try it out. And next to their courses, they also have a very active learning community over there, so you can post own questions there or answers to previously asked questions by users, and it's just really good. It's a very nice community, and it's actually partitioned also into difficulties, so you get easy exercises, medium difficulty exercises, and so on. And if you want to learn something that isn't yet on their website available in the course, there's probably something in their community as well that you can try out. So it's definitely worth giving a shot, and if you feel like this could be something for you, then make sure to check out the link at the top of the description. With it, you're going to get free access to a big portion of Brilliant already, and the first 200 people to actually make use of the link get 20% off an annual premium subscription, which is a great deal, like mentioned before, considering how much content they have available on their website already. And since they are increasing the amount of courses each and every month, it's even more worth to get yourself an annual premium subscription, just to see where they are headed, what they are going to add next, or maybe what they are going to change on previously created courses, because this is something that they do too. They update courses, for example. So they give a lot of thought to their website, and just overall it's a pretty good experience even for me, and I just love their stuff, and I'm really glad that they are a sponsor of this channel, and you should definitely try it out. And this basically concludes today's video, and if you did enjoy this video, please like and subscribe, recommend channel if you like, even though I'm not uploading as regularly in the last time as before. And Don't forget to check out STEMmerge 2 for cool stuff like this chaotic double pendulum, and maybe for the NG watch. With it you can mock engineers like a real mathematician would do. And up until next video, I wish you guys a flammable day. Ciao!